Okay, so we have a midterm exam coming soon. Chapters 1 to 5, it is on next Wednesday during the lecture time. So keep that in mind, right? So you guys should be studying around now, right? And most of you already have been studying, which is good. So that is our midterm exam next Wednesday, 25th of November. So it is the Wednesday of week 8. Today we are starting week 7. And also another thing to mention to you guys is I given you your quiz scores already, so it is in the grade book. To check your score for quiz 1, right? You go to the grades on the left here, and then you can check your score here. So as you can see, I got 0 for quiz 1, but you guys will have higher marks. Then yeah, so that's the two things to mention. And I guess if there's no other things to talk about, let me get started with calculation of moments of inertia. So you guys want to see how to derive the moment of inertia for a uniform sphere, right? So based on the picture, the list given in the lecture notes, the moments of inertia for a uniform sphere should be 2/5. So it is a solid sphere. That means inside is not empty, it's a field. This is different from the hollow cylinder. Hollow cylinder inside is empty, so it's only got a shell. So this one, we are going to calculate this, right? So how do we find the moment of inertia for the uniform sphere? So let us try to work this out. Okay, yeah, let us try to work this out. We are here already. Okay, so now the idea for the uniform sphere is that we can cut this into many slices, and each slice is one disk, and we know we already calculated the moment of inertia of one disk, remember, right? We have done that last week. So what we're going to do is we're going to use that information and build up the sphere, the solid sphere. Okay, so I should emphasize this is a solid sphere. Okay, so how to do this? So let me put the coordinate system where the origin is the center of my sphere, and this is my z-axis, and then I cut this up into many slices. So for just take one example of a slice, I have one slice here, right? So this is one disk. The big R is the total radius of the sphere, but if I'm up here, right, the radius of this disk is smaller compared to big R, and we can actually calculate, because if this is theta, right, and then this is R, then we can actually use trigonometry to calculate. So to help us calculate, right, we are going to look at the z coordinates of the sphere. So the z coordinates of the sphere is this, right? So what is the z position, right? So there's some z position over here. Z coordinate of the disk is what? Well, we can actually calculate. This is z is equals to what? This is the big R, right? This is the total, the full radius of the sphere. This is the angle theta. So the z is the height over here. So therefore z is equals to r cos theta, right? So very straightforward, r cos theta. And then what is the radius of the disk? Okay, so the radius of the disk is this one. It is so this one you have to be careful. It's not the big R, right? It is some R, and it should be smaller than big R. So from here we can see that this is a triangle. So the radius of the disk is r sine theta, right? So it's r sine theta, right? This R, this is theta over here. And furthermore, we notice that, okay, sine theta is the square root of 1 minus cos square theta. So if I put the r inside, it's r square minus r square cos square theta, and then we take the square root. So r cos square theta is the z coordinate of the disk. So this is just z square. So in other words, I have found the formula for r, which is very straightforward in terms of the z coordinates, right? So we got this now. Okay, then how do we so before I continue getting the moments of inertia, let us try to go through some concepts and make sure everything is correct. For example, what is the area of the disk, right? I'm going to use this to derive the volume of the sphere, so we will see, right? So area of the disk is what? So area of the disk is, by right, is pi r square, right? So what we got is pi r square minus z square. Okay, so that one no problem. What is the thickness of the disk? Okay, so the thickness is is just dz, right? So it's nothing much there, dz. So therefore from here I can get the volume of the disk. Okay, so since this is an infinitesimal slice, the volume is a very tiny volume because it's so thin, right? It's almost close to zero. So it's basically just the area times the thickness. Right, so from here we find that the area was pi r square minus z square, and then the thickness is just dz. So this is the volume element of the disk. So we are going to use this later, so I will keep this in mind, right, and draw a box around it so it's easy to find later. So we want, this is the infinitesimal volume of the disk. Now what we want to do is, let us check our concept, right? So this is infinitesimal volume. So if I sum up all the volumes of all the disks throughout the whole sphere, I should get the volume of the sphere. Volume of the sphere you learn in high school is 4/3 pi r square, right? Pi r cube. So can we get 4/3 pi r cube or not? Let's double check, right? So which is to say that let us see whether everything is correct. Total volume of the sphere should be equals to the sum of all the disk volume. Okay, just that the only problem is that each disk have different volume because each disk have different radius, right? So starting from 0 radius and then enlarging, and then here come back to small again. So if I sum up all the correct radius of the disk, I should total up all the volume and get the actual volume is expected to be 4/3 pi r squared. So let's see whether we can do this. So volume of the sphere is the sum of all the volumes of the disk, which is to say that I want to integrate r square minus z square with respect to dz. So what I want to compute is the integral. The constant pi, I take it out, right? And then I'm just integrating r square minus z square, integrating with respect to dz. So now that I have formulated the integral in terms of the z variable, I can decide the limits. So I'm integrating from the lower limit to the upper limit, right? So the lower limit is negative r, upper limit is positive r. So this position is positive r, this position is negative r. So from minus r to r. Okay, so just perform this integral. Now, the MAT student already know this, right? You've gone through calculus 1. The physics students who are taking calculus 1 now, probably just about starting integration soon. So I don't know if you know this. To make your life easier, right, we want to make use of the concept of the even function. This is an even function, right? So if this is an even function, right, you will learn in calculus later if you haven't already learned it. Instead of integrating from negative to positive, I just do 2 times, and then I just start from 0. Okay, so do you know this? Okay, so just need to integrate it in this way and integrate this with respect to dz. Okay, when you have a 0, the integration is so much easier, because if you just keep it like this, right, you will get the correct answer, but it's more troublesome because there's an r here. You need to manipulate more things and wasting time, right? So what you have now is, well, I just need to integrate this. So I got r squared z and then 1/3 z cubed from 0 to r. So the lower limit immediately make everybody zeros, which is nice. And then I got 2 pi, and if I plug in the upper limits, I got r3 minus 1/3 r3. So this part will give me 3/3 minus 1, it will give me 2/3 r3. So 2/3 times 2, yes, it will give me 4/3 pi r cubed, which is the volume of the sphere. So we have confirmed our volume integral. Okay. Okay, any question? Everyone follow so far? Okay, we are just getting started, right? This is just the volume, haven't even started moments of inertia, which we will now do next. Okay, so how to find the moment of inertia of the disk? Okay, so let us try to work this out. Okay, any question? The even function, how to see? That one is, yeah, that one you ask your calculus, right? For even function, f minus x is equals to fx, right? So anything with a square, you negative sign, you make it positive, right? So yeah, this is the calculus. So for odd function, f negative x is negative of fx. Okay, so if the function doesn't satisfy both either of these conditions, then it's not even and it's not odd. But this is an even function, right? So yeah, so here is z lah, z. Okay, any other question? Okay, if not, let us see how to find the moment of inertia. Okay, so the moment of inertia is the following. Okay, hang on, right? So the moment of inertia okay, where am I? It's not here, but never mind. For the moment of inertia, right, we are talking about a uniform sphere. So uniform sphere, when we calculated the moment of inertia, right, what did we want? We want a dm, right? So a uniform sphere, that means this is a three-dimensional object. So dm dv is equals to the density, and it is a constant, right? So it's a this is a uniform sphere. So which is to say that rho is a constant. Okay, so what is my formula for this thing? So we got this and then dv, right? And our dv was all this stuff over here, so which is pi rho pi r square minus z square dz. So the total mass is the integral of dm, right? So it's the integral of rho pi r square minus z square dz, right? And what we have here is just taking out the constant and r square z square dz, but we just did this integral, right? So from minus r to r, and this is the volume of the sphere, which we found to be 4/3 pi r square. We did this just now, right? So in other words, we have found rho. Rho is just mass over the total volume of the sphere, so 4/3 pi r cube. Okay, so this is what we expected again. This is a uniform sphere, so it's the same as, the density is the same as total mass of the whole thing divided by the total volume of the whole thing. Okay, so this is the uniform sphere. So therefore, now I can express my dm now. So my dm is rho times this thing. So dm is equals to rho, which is m over 4/3 pi r cube, and then this thing, which is pi r square minus z square dz, right? And then notice that pi and pi will cancel. There's a 4/3, so the 3 bring it up to make it more convenient. So I got 3m over 4r3 and then r square minus z square dz. So this is the mass element of the uniform sphere. So now we got my dm now. Now let us try to calculate the moment of inertia of a sphere. So moment of inertia of a sphere is just the sum of many disks, moment of inertia. Okay, so and then what was the disk, right? So for one disk, right, the moment of inertia of one disk, what did we calculate? It was a half, right? Half mr square. So it's a half m r square from the radius of the disk. So therefore, for infinitesimal mass dm, so if the mass is very small, this moment of inertia also will be very small. So a tiny mass will give you a tiny moment of inertia. Okay, so we got that now, and then which is to say that the moment of inertia of the whole sphere is the sum of moment of inertia of a disk, right? And then which is to say that is this, so it's got half dm r square. Okay, so does everyone follow so far? Okay, not too fast, right? Because we have been doing a lot of the similar calculation in the previous week. So now we are ready to actually calculate, right? So firstly, the moment of inertia of the disk is integrating over dm. The expression for dm is here already. Okay, so we put this in. And what was r? We also got r just now. The r is the radius of the disk, is this expression. So r square is equal to big R square minus Z square. So we're going to put this in as well, right? So once we put all our ingredients in, we can perform the integration. Okay? So it's fine, right? So now let's see what happens to our integration. So what we have now is I is equals to the integral of half times this. So half times 3m over 4r cubed, and then r square minus z square, and then dz. Okay, dz. And then there's a r square at the back. So there's another r square minus z square. So this is two things square. So let us rearrange. Well, these are constants, so might as well take them out. Right, so I got 8r3, and then I'm integrating r square minus z square, integrating with respect to dz. Okay, so to make it easier to integrate, it's up to you how you want to do it, but I prefer to open up the square. So I got r4 minus 2r square z square plus z4 integrating with respect to dz. So the term by term, these are monomials, so these are easier to integrate, at least for me, right? And the limits of integration is from minus r to r. Okay, but this is also still an even function, right? So all the z has even powers. So since this is an even function, I got 3m over 8r3, and then 2 times starting from 0 is enough. Okay, so I got r4 minus 2r square z square plus z4 integrating with respect to dz. So cancelling the 2, I got 3m over 4r3, and then integrate this thing. So integrate this thing, I got r4z minus 2/3 r2z3, right? And then integrate this becomes 1/5 z5 from 0 to r. Okay, so see, when you change it to 0, right? Everyone here 0, so the lower limit no need to calculate. You cut down half the job, right? So less work to do here. So all you have is r power 5 minus 2/3 r power 5 plus 1/5 r power 5. Okay, so everybody has r power 5, so I can take out r power 5, and then basically I have all the fractions, so I can make everybody over 15. So this is 15 minus 10 plus 3, right? And then r power 5, took it out, right? So this is 5 plus 3. First, so this one must be careful. Okay, so this is 5 plus 3, so I got 8 over 15. And what we seem to have is 4 cancel, it becomes 2. 3 cancel becomes 5. And then r3 and r5 cancel become r squared. So I'm left with 2 over 5 mr squared, right? So we confirm the formula that was given in the table. Okay, you follow so far? Everyone okay? Any question? Okay, no, so if not, then yeah, so that is the moment of inertia of the solid sphere. Okay, so now let's do one more moment of inertia calculation, and then we shall go to chapter 6. We will start chapter 6 today. Okay, but just one more thing, the moment of inertia of I want to calculate the disk with a hole. 2/5 mr square, yeah, 2/5 mr square. So we have confirmed this formula. So 2/5 mr square for the solid sphere. Oh, I see what you mean. Yeah, this is square. So yeah, the units is kg meter square, so it should be square. Thanks. Okay. What time is it now? 10:20. Maybe I just go straight to chapter 6. I feel like we've been spending too much time doing moments of inertia. Okay, so let's do chapter 6, and then if there's, let's see how far we go with chapter 6, and then if there's enough time, I will come back to this. Okay, yeah, because we shouldn't spend too much time calculating moments of inertia. Okay, so let's go to chapter 6. We start a new topic, rotational motion. It's actually not a new topic because this is part 2 of what we have been talking about. Okay, so we are talking about rotational motion, and the thing that we want to talk about here is firstly torque. Okay, torque. So torque is the, now what we have been learning so far, right, is that when it comes to rotational motion, we have been carrying over all the concepts from linear motion, right? So for linear motion, we talk about displacement, right, change in position. Then in rotation is angular displacement. For linear motion, we have velocity. Now we have angular velocity. So acceleration, then now we have rotational acceleration, which angular acceleration. Okay, and mass becomes something like a moment of inertia, and kinetic energy, we have rotational kinetic energy. So everything carry over. So now this one we are doing it the same thing but for force. So force is for linear motion, for rotational motion is torque. It is something that causes angular acceleration. Okay, so that is what we want to talk about today. So this is the torque, T-O-R-Q-U-E. Okay, so torque is a kind of force. It came from a force that causes rotation. Okay, so that is our torque. So what is the definition of a torque? So let me define it by the original definition, which is in vector form, and is defined in terms of a cross product. But if you are scared of a cross product, don't worry, we seldom use the concept. Okay, we seldom talk about the cross product. We mostly deal with the magnitude and then the direction, which we can determine from other way. But at least I should show you the official definition first. It is the cross product between the position and the force. So what is R? R is the position, F is the applied force, and of course this is the linear force. Okay, and R is the position where F is applied. Okay, so what does that mean? Because remember, right now we are talking about rigid bodies. Rigid body is something where the size of the object is important. So if you have something, right, with a certain size, okay, so let's say it's fixed at the axis here, so it's some wheel, and you exert a force on it. Last time we have been treating everything like a point particle, so exert force, you get acceleration, or if it doesn't move, that means there's some force that cancelling. So that is the linear case. But if you care about the size of the object, right, then it depends where you push it. So if I push it here, it will rotate in the anti-clockwise direction, right? But if I push it the other place, it will now rotate in the opposite direction. So the location where you apply the force is now important, even though you have exactly the same force. So let's say I exert a force of 10 newtons upwards, right? If I exert it here, it's going to rotate this way. But if I exert the same force, 10 newton, same direction upwards, 10 newton, if I exert it here, it will rotate in the opposite direction. So the location where the force is applied is now important. That's why a torque depends on not just F alone, but the where you put the F, right? So where you put the F. So that is how you describe the torque. So let's say I am applying the force at some direction, right? So let's say my F is this way. Okay, so this is my F vector, and then the position where you applied the force is, if I put this as my origin, then this is the position where I applied the force. This is R. So the angle between the two vectors is this phi over here, right? So this will tell me the magnitude and also the direction. Now, torque is a vector. You need to know what is the magnitude and direction. So the direction, okay, so the direction is determined by the right hand rule. Okay, so in this example, right, what is the right hand rule is, I take the vector r, okay, and then important thing is I need to join the tail, so I move the r here, okay, and then right hand rule is I take my hand to the first vector and then I close it to the second vector, which is f. So r cross f, the first vector is r, and then I close it to f, and then the axis of rotation is pointing up, okay. And remember the right hand rule. The right hand rule is, this part also tells you the direction of rotation. So if I cross it like this, this is rotating in the anti-clockwise direction. So that means this object will rotate it in this way. Okay. Yeah, I mean omega or alpha. It should be more alpha, right? So the direction is by, you can determine the direction using right hand rule. Do you understand what I just said? Okay, hopefully everyone understand. If anyone don't understand, say something for me to explain again. But if you understand, let's move on to the magnitude. Okay, so the magnitude is, the magnitude of torque is given by this formula. It's just the magnitude of r times the magnitude of f, then sine of the angle between the two. So usually to save time, we don't want to write so many things, right? We just call this tau without the arrow, r without the arrow, and f without the arrow, and then sine phi. Okay, so this is sine. So in particular, if the angle between the two is 90 degrees, right, then torque is just r times f. Okay, so if phi is 90 degrees or 90 degrees, then torque is just r times f. That's all. Okay, so it depends on where you exert the force, right? Just to make it even more clear, right? What happens if I take the same force, okay, but I exert it here? Okay, in fact, I can exert it on a different point. So I take the same f, I put it here, and then this time my position vector is r2. Okay, so this is my new angle, so let's call this theta, right? And then I use my right hand rule, right? So if I don't put my force here, if I exert my force here, right, if I push the thing from here, what is the right hand rule? Take the first, so my right hand goes to the first r, so first r, right? So if I try this way, I cannot go to f by close my, I cannot go to f this way, cannot. So I need to flip my hand, and then I can now close my f in the other way. So my axis of rotation is pointing down and is now rotating in the clockwise direction. So you can use this to get your right hand rule. Okay, so did someone have a question? Is the f always tangential? Yeah, no, it's not. Not necessary. Depends on how you theta, because f is like however you want to push it. I can purposely push like this or like this or like this, right? So yeah, not always tangential, but very frequently it will be tangential if it's 90 degrees. Correct. Right hand rule always from r to f. For cross product, right, it's always the first vector, right hand from the first vector to the second vector, your right hand. Okay. Any other question? Yeah. Okay, so yeah, perhaps let me yeah, just to, I think this is a new concept to many students, right? This is not something that you learn in high school. I don't think so, right? So let me draw some more pictures and make and see how to, let's try to understand this a bit more. Okay, so let me draw a different viewpoint. Okay, so let me draw it from this viewpoint. Okay, so this object is fixed here, so this is my axis. Okay, and then let's see, right? So let us practice our right hand rule. So let me take a force and then I push it here. Okay, so I push my force here. what is the torque. From this picture and from our imagination, right, we can imagine if I push something this way, it will cause it to rotate in this direction, right? But how do we get from the right hand rule? So we need the R. The R is the position from the axis to the location where you applied the force. So this is R. And to calculate the right hand rule, I need to start by the tail. Let me move the vector R outside so that the tails are together, and this is my magnitude. Okay, so if I use my right hand rule, okay, if I use my right hand rule, I need to use my right hand to the first vector. So the first vector is R, and then you go to F, the second vector, right? So R is how to do this, like this, right? And then I close it to the F. So in this three-dimensional picture, in this viewpoint, right, my axis of rotation is here, and then my direction of rotation is like this. So it is anti-clockwise, right? So then my torque R cross F is pointing this way. So it's it's this way. Okay. So which is to say that the direction is anti-clockwise. Okay, so if I draw it from another viewpoint, actually the torque should be along this axis. Yeah, then it makes more sense. Okay, so if I draw the same picture, okay, and then I apply the force somewhere else. Let's say I apply the force here. Okay, so let's say this is some force, it has some direction. So let's say the direction is here, the magnitude is the length, right? And then my axis is here again. And then how do we get the right hand rule? So this is my position from the axis to the place where you apply the force. So let me move the vector up so that the tail to tail gives the correct angle, right? So this is my vector. And then if I use my right hand rule, okay, like this cannot right hand rule, cannot, right? My F is the other side, so I need to flip my hand and then I close it. So if I flip my hand and close it, my thumb is pointing down, so my axis for the torque is pointing down. And if I'm pointing down and look at my finger, right, my finger says it's rotating along this direction. Okay, so this is the using the right hand rule. And again, if you want to get the magnitude, you find what is the angle between the two. Then the magnitude is just R times magnitude of R times magnitude of F sine phi, sine of this angle. Okay. A lot of the question end up to be 90 degrees because it's just how forces work. But depends on, it could be anything. Okay. So what is the dimension of torque? Okay, so the dimension of torque, well, the torque is given by R cross F, right? It's a vector, but the dimension, we don't care the vector, we just look at the units, right? So the unit of R is just the length, right? And the force is just mLt minus 2, right? So what we got is ml squared t minus 2. Okay, so this is the dimension of the torque. Okay, and then the units is, well, you can say that this is kg meter square second minus 2, but F, right, mLt square is Newton times a length, so you can also say that is Newton meter. Okay, either way is fine. Okay, so does everyone follow so far? mv square. Where got mv square? Oh yeah, it's the same unit as mv square, correct? It happens to be the same, but it's not a mass times velocity square. It's just the coincidence that they are the same. Yeah, LT minus 2. It's a coincidence. Okay, huh? So now that we understand the torque, right? So let's derive the rotational version of Newton's law. Okay, so every equation that we got in the linear chapter, we have transformed it into the rotation, right? The kinematic equation, we got rotation. Kinetic energy, we got the rotational kinetic energy. Now we do it for Newton's law in rotational form. So this is 6.2, Newton's law in rotational form. Okay. Okay, so as usual, right, to make sure we really understand, we start from the simple case and then we slowly make it more and more complicated so that we can get a full picture of what is happening. So let's start with the simplest case. Just look at a one-point particle in circular motion. Okay, so draw a circle. So I have a particle that is going in a circular motion. Okay, so this is the center of a circle, right? And then yeah, so let's say my particle is here, right? So my particle is here, and then so so the radius of the circle is r, right? And let's say, right, maybe this particle is a rocket. Okay, so this particle is a rocket, and then it will when you shoot the rocket, right, it will exert a force that is tangential. So now I'm really considering a case where it's tangential. So the tangential velocity we have found, right, it is r omega, and it will also have a tangential acceleration. Okay, so got a tangential, and then there's a r over here, right? So and yeah, so let me remind you guys, v tangential is r omega, right? So this is the tangential. Then the a tangential is just the differentiation of r and omega, and this is in a circular motion which is constant r, so it's just d omega dt, and this is what we found last time, right? So the tangential acceleration is r omega. Okay, so now let's look at the tangential component of the force and the acceleration. Okay, we have spent so much time working out the centripetal radial component, right? But now let's look at the tangential component. So by Newton's law, right, F is equals to mass times acceleration, right? So along this component, and we have found that A tangential is r omega, so mr alpha. So I got, yeah, this one becomes alpha. Yeah, correct. you noticed it, yeah. Oh yeah, you said like related to energy. Not really. We will actually come back to energy again, right? So yeah, so not really. The reason, I guess a brief answer to your question, right? Work is definitely energy, right? And we will talk about the work done. So the units of torque has the same units of energy, because if to get the work done, right, is integrate tau d theta. Theta is dimensionless, right? Angle has no physical units, so that's why it's the same dimension of energy. Okay. Yeah, so torque is a bit weird in this sense. What were we doing? Oh, we are doing this, right? So we say that F tangential is equals to mr alpha. Okay. Now, what is the torque acting on a particle? So if it's experiencing a tangential acceleration, right, that means it has a tangential force. So tangential force, then if force times the distance will be the torque. So if I times r, right, and 90 degrees, so sine 90 is 1. If I times r on both sides, I got this. So from this part, this will give me the torque, and this part is the moment of inertia. So this is actually the moment of inertia alpha. So from here we got the Newton's law in rotational form. The torque acting on a rotating object is just I times alpha, right? It's similar to F equals to ma. right? But now the F changed to the rotational form. The M in rotational form is like I, A in rotational form is alpha. Okay, but otherwise everything else it looks the same, right? The way we use it is going to be mostly the same as well. Kinetic energy is related to work energy theorem. Yes, correct. Yeah. So this is the same dimension as kinetic energy, same dimension as work, is in joules. Okay, but for torque is this thing. Okay, yeah, we will come to that later. Right, we will derive the work energy theorem for rotations. Okay, so any other question? Right, so for a single particle, right, so this is the Newton's law in rotational form. So we just done it for a point particle. Now let's do it for a rigid body. Okay, so the rigid body is just a collection of many particles, so that one is nothing special. So we just carry over our results from a single particle. So a rigid body, right, is basically consisting of many particles of infinitesimal mass dm. Okay, so infinitesimal mass dm. Okay, so let's look at some rotating disk, right? Some rotating disk, so something like this, top-down view, right? So the axis is over here. So it consists of many points, right? So many points, right? Let's look at one point. So one point is having a mass dm, and for this one point, the radius is some r, okay? And this one point is going its own circular motion at this. But if this is a rigid body, the whole thing must have the same omega, right? So everybody is rotating at the same angular velocity. Now, because of what we have been saying, right? If there is some force, right? If there's some force that make it turn, that means each particle must be experiencing some tangential force, right? So each particle experiences a tangential force. Okay, so the mass is dm, right? So it's the same thing. A particle that is, if it's going right, and if it's experiencing some tangential force, is spinning faster and faster. That means by Newton's second law is having this equation. But if the mass is dm, very small, then the corresponding force should be also very small. So the infinitesimal tangential force is equals to infinitesimal mass times the tangential acceleration. Okay, so then we do the same thing as we did just now, which is to replace A in terms of R alpha, so that my df tangential and then R alpha and then dm, right? And then we multiply both sides by R. Okay, then we have R df tangential. So I'm assuming that, well, this is the tangential component, right? If the net force is not purely tangential, there's some component, but we only take the tangential component, right? So we got R square alpha dm. Okay, so yeah, so I should rearrange one more time, because the R square dm, this part is like a moment of inertia, right? And then alpha. So this is the infinitesimal torque. And this is the infinitesimal moment of inertia. And then this is just alpha, right? So the torque is equals to di alpha. So this is for one particle of mass dm, and of course to get the total for the whole object, then the total body is the sum of all the infinitesimal. That means if I want to get information of the total torque acting on the object, I need to integrate the tau, so I integrate the I alpha, right? So so from here again we get tau is equals to I alpha, because I'm summing up over all the whole object, alpha for every point should be the same. It's a rigid body. Rigid body, the whole alpha for everybody have the same alpha, so alpha is a constant in terms of the position, right? So here is alpha may not be constant in time, of course, but for a snapshot of time, different position have the same alpha. That's why alpha is a constant with respect to position. Okay. Respect to position may not be constant with respect to time. Make sense? Okay, what time is it now? Any question? Okay. So we have derived the rotational version of Newton's law already. So now we can actually start solving rotational problems involving torque, which is what we are going to do next. Okay. Why don't we say it's a coefficient? Where? You mean alpha? I mean, technically it is a coefficient, but yeah, it's something multiplying. Is that what you mean? Okay. Yep, it's odd. I mean, well, is alpha is a coefficient to I in the same way that a is a coefficient to m, right? Yeah, you can say, but it's not wrong, but is changeable direction. Yeah, alpha. Okay, so alpha is different for different situation. Okay, so that's what you mean, is it? So for a single body, moment of inertia is always I, right? It's just the same thing all the time, but you can accelerate at different depending on the situation. So alpha is the coefficient, right? So alpha is the variable here, and the tau is the independent variable. Wait, I think something is going wrong with my thing. My screen is frozen. Wait, let me. Hello? Hi. Can you hear me now? No, my screen is not okay because see, I'm moving my hand across my visualizer and my visualizer hang. So let me try to restart. Turn down the volume. Okay, now I'm restarting my visualizer, turning it on again. Test 1 2 test. Okay, the screen is still frozen. old piece of technology that is big and heavy. Is probably more than 10 years old. Okay, so yep, can see, everyone can see. Yeah, low budget. FPS quite high. Yeah, that's true. That is one good thing about it. FPS quite high. I would say about 30 FPS if I'm looking at it on my screen. So I mean, yeah, probably lower than 30. I don't know. Okay, so let's work out an example. I'm sharing my screen, right? And now let's see an example. So chapter 6, lecture notes. Okay, so we're going to do this, right? Well, 10 years old doesn't seem so old suddenly. I guess so. Oh, your high school. Wait. Oh. Now my mouse suddenly acting weird. I use my touchpad again. Oh yeah, so your high school one 10 FPS. Yeah, definitely. This one is, I think, not 720p. It's a 4:3 ratio, but it's quite high resolution now, so it's comparable. Okay, so Charles, you need to remember for a point particle, what's the moment of inertia of a point particle? Mass times r squared. That is the point particle. Yeah, my computer doesn't seem well today. I don't know why. So we are going to do 6.2.1. Okay, but this is the same situation as same system as what we did for a previous chapter, example 5.5.1. But now we are calculating different thing. Okay, now we're talking about the torque of the system. My computer got COVID. Maybe, huh? Computer COVID. So, wait, am I recording? Just double check one more time. Test. I'm recording. And I'm recording here. COVID. Yeah, COVID-19. COVID-20. Okay, I have two full screens. No need. Okay, so now hopefully everything works for now. So let's solve 6.2.1. We have a light stretching cable. Okay, this one comes up. We have a light stretching cable wrapped around a solid cylinder of mass 50. So yes, usually it helps, since it helps to just write down the information as we read along. So the mass is 50 kg and then the diameter is 0.12, so the radius is 0.06 meters, right? Remember to divide by 2, and then it's being pulled by a force of 9 newtons. So just like last time, right? And over a distance of 2 meters, and it unwinds without slipping. We just want to find the cable's acceleration. So it's being pulled at constant force over a distance of 2 meters, and I want to find the cable's acceleration. Okay, so you guys are talking about computer COVID, right? So let me just finish the question and then I check what you guys are saying later. But for now, let us try to understand this question, right? The question says that the thing is unwinding without slipping. So remember, what did we mean when we say without slipping in this context? Without slipping and also inextendable string, in non-stretchable string. Okay, so what do this means? So this means that the force at the end of the string is the force being exerted on the string, but then it will become the tension of the cable, and because the tension of the cable is attached to the cylinder, so it becomes the tangential force on the cylinder. So if I times R to this tangential force, it becomes the torque. Okay, and then also for if it's without slipping, then the tangential acceleration at the cylinder relation at the cylinder's edge is equals to linear acceleration of the string. Okay, so which is to say that we can use the Newton's law for rotational motion. The torque is equals to I alpha, right? And because the tangential force is the same as the string, so it's just R times F, right? Where this is 9 newtons. This is a cylinder. We have spent so much time calculating this. This is half mr squared. And for alpha, right? So alpha is the A tangential over R at the cylinder. But according to the this is not slipping and non-stretchable, then the A tangential is equal to the acceleration of the string. Okay, so now we can do a lot of cancellations. R cancel here and here also cancels. So the F is equal to half big M and then the A of the string. Right? So now we can actually calculate the acceleration itself. It's just 2F over M. So it's 2 times 9 over 50 kg. So it's 0.36 meters per second square. Okay, so this is the acceleration of the string. Okay, so what are you guys saying? Oh, yeah. So students who are in China, they don't understand Malay, right? Kena means God. Yeah. Recording for Teams has stopped. Really? It's still running for me. It's still running. Yeah. Yeah, recording didn't stop. Yeah, so oh, is it? You press start lah? Yeah, okay, great. Thanks. How about over here? Yeah, so why is everything acting strange today? So thanks, Jiasheng, for recording. And I think last time, was it Ka Heng who helped me record also? So thanks to Ka Heng for last week also. Was it? I don't remember who. Yeah, I think it was. But yeah, today the system is very unstable. Let's try to push through. So yeah, so we found the cable's acceleration, which is A. Okay, so that's what we got over here. Yeah, so hopefully, the virus is finished soon. Then the students who are in China can finally come to Malaysia and they will experience the weird Malaysian stuff, the Malaysian language, English, Malaysian food, Malaysian weather, right? So those who are in China have not come to Malaysia before, is it? Yeah, it will not be soon, but hopefully before you guys graduate. Wait for vaccine. Yes, that's true. So a light non-stretching cable is wrapped around a solid cylinder of, wait, we just did this. I'm talking about the next question. Okay, a light non-stretching cable still wrapped around the cylinder, but now it's vertical, right? So I have a mass M and the radius of the thing is R, and the thing will drop, right? So now this is where it starts to get tricky. So this is a basic question. So let's try to pay attention or like let's try to understand the fundamental methods that is at work here. So what we have here is a cylinder rotating with negligible friction, stationary horizontal axis. So it's just describing this picture. The free end of the cable is attached to a block. This block is having mass little m. This cylinder is having mass big M. The radius of the cylinder is capital R. So as the block falls, right, it will unwind and it will continue coming down over here, right? So it will be experiencing some acceleration. And from here, we want to calculate the acceleration of the falling block and the tension of the cable. Test. Okay. Yeah, you guys saying, talking about getting negative inertia, right? Which, why? Wait, I didn't read all the messages, but hang on. Let us finish this before the system breaks down again. So how do we solve this system? We want to find the acceleration and the tension of the cable. So let's do it one by one. Now we start to combine our concepts. I have a box that is going straight down. So this is a linear motion. If it's a linear motion, I can do it the usual way. I can draw the free body diagram of the box. So free body diagram of the box, what is happening with the box of mass m? It is attached to a string, and as usual, we got a tension T, right? And then it has a weight, we got a mg. And if I take down as positive, then the net force is mg minus t. It will give me the mass and acceleration of the box over here. So this is the equation 1, right? So I don't know the acceleration, I don't know the t. The question asking us to find both, so there are two unknowns. I need a second equation. So for the second equation, let's look at the cylinder. So now we look at the rotational motion. So let's look at the torque on the cylinder. So what's happening with the cylinder? So for the cylinder, right, it is a cylinder of radius r. It is attached to a cable that is unwinding, so there is a tension T coming over here. Okay, so if I use first of all, let me say anti-clockwise is positive. Then we use Newton's law. So my torque is I alpha. You see, the torque has a cross product definition, but don't be scared because we seldom use the cross product right hand rule, right? We just say, okay, anti-clockwise positive, magnitude, fine. Then that's good enough already. So what is the magnitude of the torque? So this T is 90 degrees to the radius where the T is applied. So I just want to say T times R gives you the torque. And this is a solid cylinder, so the moment of inertia is half mr squared. Okay, so alpha, right? So I cancel this, and from here I find that T is equals to half mr alpha. Now let's look at alpha. So the cable is also no stretching, no slipping. So that means the linear acceleration that is moving the box is the same as the tangential acceleration at the edges of the cylinder. So A is equal to tangential acceleration is just R alpha, right? In other words, alpha is A over R. Okay, so if alpha is A over R, then we can put this in. From here we find that T is equal to half mr A over R. So I can cancel the A. We find that T is half ma. Okay, so I got equation 2 over here, right? So from here I can now find, I have two equations and two unknowns. So I can solve to find T and A. Anti-clockwise, yes, anti-clockwise. Sugumaran. Negative inertia. Okay. Interesting chat you guys are having. So now we have two equations, two unknowns. Then we can solve for, well, we can solve for A first because I can easily take equation 1 plus 2. So 1 plus 2, the T will cancel each other. So mg is equals to ma plus half big M times A. So if I multiply everybody by 2, right, so I got 2 little m g and then 2 little m A and then big M A. So I got find my formula for A is just 2mg and 2m plus big M. Okay, so I got this thing over here. Then from here I can get my tension. It just comes out equation 2. So tension is just half ma, so it's just half times m times this. So T is just half ma, and we got this a already, so it's just mg over 2m plus big M. Okay, so I got my tension and I got my acceleration. Okay, so this question is still straightforward, but the fundamental method is there. And when it comes to later questions, right, it becomes more and more complicated and students find more and more challenging. But at the end of the day, you still need to draw some free body diagram, identify the forces. At the end of the day, you figure out the torque on the cylinder. All right, everything is still there together. Okay, so it's basically this fundamental method. So using this, you can solve all the questions already. Okay, yeah, so how's everyone? Is there any question? Huh? Python? What? Sugumaran is your Python lecturer? Is it? Wait, did I answer your question? Yeah, so the word I'm writing here is anti-clockwise. And what else? Yeah, so the rest is just calculation. Okay. Okay, so that's torque, right? And basically that's how we solve questions involving torque. And there's going to be more questions in the tutorial and so on. Okay, so let me check again. What time is it now? Okay. Oh, Kaheng wants to see the last few lines. Hang on. Yeah, it's over here. Let me see the messages through my phone. Oh, use Python to make moment of inertia graph. Yeah. So from my understanding, yeah, Python can visualize a bit upper. Oh, you mean the previous page? You mean this? Okay. Yeah. Yeah, so Python can plot graphs and things like that. There's many software and you know, as you go through your physics program and career, you might learn more and more software. So right now everyone is starting with Python, which is good. And there's things like GNU plot, you know, and if you have the chance now, you learn LaTeX if you can. Okay, done. Yeah. And things like that. Okay. So now is okay, so we have about half an hour left. Let's talk about work. So yeah, was it Zirui who noticed that the SI unit for torque is the same as mv square, which is the same as energy, and we see why. Okay, so let's look at work done in rotational motion. How's my sound? I don't trust my hardware now. Test. Recording sounds good. Okay, thanks. Okay, so looks like good. This is section 6.3. Okay, so we are talking about work done in rotational motion. Okay. Yeah, so let's look at some rotating object, right? So let's draw some object here. So this object is rotating. So if it's rotating, right, so let's say it's experiencing some force. Okay, so this is a tangential force. Okay, and because of the tangential force, right, just like work done is I have a block and then I have a force that it will push over some displacement, right? So if I have a box and then if I push it, it will work done, force times displacement. But now the displacement is angular, right? So if I exert a tangential force, it will rotate by a certain amount. So let's say the amount of rotation is infinitesimal, is d theta, and the displacement caused by the rotation. Let's say if I look at this object, right, it will displace by a certain amount, so by amount of ds. Okay, so what I have just drawn here is a tangential force acting on a rotating object. Okay, rotating body. Okay, so to derive the rotational work done, let us start with the concept that we know, the linear work done, right? So let's say I have some point here, and then I push the force, and then it will displace by amount of ds. So we have the work done over an infinitesimal rotation, over an infinitesimal. Well, let's talk about the displacement first, right? So infinitesimal displacement. Okay, so is the work done is just basically the force times the infinitesimal displacement. Okay, and so this is the linear case, right? So this is our using our linear equation for the work done. But to express in terms of rotation and torque, right? Let's look at this. So we are using the fact that ds is equals to r d theta. I hope everyone knows why by now. Okay, so I substitute this into here, right? So I'm going to replace ds in terms of r theta. So what we have is f is equals to f tangential, and then r, and then d theta. Okay, so this is the tangential component of the force. So the torque is definitely 90 degrees. Tangential is the 90 degrees part. Then we notice that F times R is the torque. Okay, so the magnitude of the torque, the direction, we can say what's the direction later. But in any case, this is our torque. So the work done is torque d theta. Then the total work done over the whole process should be the integral of all the infinitesimal amounts, right? So it's basically integral tau d theta. So the work done is the integral of tau d theta. Okay, so this is the rotation work done for rotational motion. Okay. Yeah, differential. It's not straight, but if S, yes. So the reason why I can use, right, I want to argue is that the displacement is very, very small. So it's a curve, but if it's short enough, it's almost straight. If it's almost straight, then we can say it's ds, then almost like a linear equation. Okay, make sense? So let's come back to the thing about the units, right? So this is now we have derived this from the usual work done, and is the same unit. So let's look at the dimensions and units, right? So the dimension of work done is the dimension of this expression, right? So it is basically the dimension of torque times the dimension of angular displacement. Okay, integral doesn't matter, right? Because we're talking about just the units. We just want to look at the units. So the torque is what we got was mv squared, right? So ml squared t minus 2. Angular displacement has no dimension, right? Angle and radians, degrees and radians it's just a degrees and radians. They are not physical quantities. Okay, it's just angles, right? So it's no dimension, so it's the same thing as m squared t minus 2, right? So it's yeah, so it's the same thing. 1 joule is kg meter square s minus 2, and it's the same as the linear work done, right? So everything is the same. It's the same work done. So if you're calculating work done on a system, right, the total work done is all the linear work done, and then together with the rotational work done. Radius times omega. Well, F is not a constant. Why not use radian? Radius times omega. Well, you can if you want. Yeah, you can. We will do that later for work energy theorem. The displacement. Oh, omega is the omega is d theta dt, right? It's the displacement over time. But for work done, we haven't come to that point yet. But we will later for work energy theorem. Yeah. So why omega is F? It's just force times displacement lah, basically. Yeah. And then plug in this to equation, correct? That's what you said. F is not a constant, although it is approximately from here to here, it is approximately a constant, right? And then remember what we did, right? We assume for a small piece is approximately a constant, then the next part is another constant, and then the next part is another constant. So you integrate over this thing, right? So F is so F becomes the torque and is no longer a constant. That's why you cannot take it out of the integral. Okay. Okay. So, but well, it's a good segue to Zuri's question because he mentioned something about omega, right? And this is what we will do when we come to talk about the work energy theorem. So, work energy theorem for rotation. Okay, so we are going to do this now. And this is where we put in omega. So, the work done we have just derived is the integral of the torque and then over this how much it turns, right? So the angular displacement. Okay, so we are going to do this integral, and we will derive it in the same way as we did in the linear case. So everything is the same, which is to say that we are going to plug in Newton's law. So we have learned two things, right? Work done is torque integrate displacement. We have also learned that the torque by Newton's second law is I alpha. So if I substitute this inside, what we have now is the integral of I alpha d theta. Okay, then we want to convert this in terms of omega. So since alpha is the rate of change of omega, we will apply the chain rule to say that the omega d theta d omega. So it's the reverse chain rule, and then I swap the two places. So which is to say that this is the omega dt, and then this is the omega d theta. So I want to substitute this into equation here. So let's call this equation 1 and call this 2. So I'm going to substitute equation 2 into 1. Okay, so by work done, excuse me. So the work done is the theta dt, right? And then the omega d theta, and then integrate with respect to theta. So this part, again, chain rule, but for integration differential, it just becomes the omega. And this part is just omega itself. So the work done, so this is W. W and omega are two different things. So this is where you have to be careful. So I omega d omega. So I have converted the integration in terms of the angular velocity, right? So remember, omega is angular velocity. And it's d theta dt. Okay, so I have expressed my integration in terms of omega. So my limit should be initial omega to final omega. So then from here I can calculate my work done. It's just half I omega square, right? And then the limits. Okay, omega 1, omega 2. So this is half I final omega square minus half initial omega initial square. And actually we have already defined this last time, right? This is the rotational kinetic energy. So the work done is just the change in kinetic energy. Okay, so now we are just talking about rotational work done. It should be the change of the rotational kinetic energy. Okay, so linear work done is the same as the linear change in kinetic energy. Rotational will be rotational. Okay. Any question? Thanks. Yeah. So everything is not everything is malfunctioning today. My computer, my visualizer, and also my body. Okay. So yeah, so everything is the same, right? Hopefully this is not too fast because it's the same thing repeating, just that instead of displacement is angular displacement. And similarly, we can also talk about power in terms of rotational processes. So the power is just the rate of change of the work done, right? And yeah, so we compute it in the same way. So we have a formula. In the linear case, is the force times velocity. For this time is the power times torque times angular velocity. Okay, so it's just the same thing, right? Nothing complicated there. Okay, so does anyone have any question? Oh, also you did this thing 2 weeks ago in the lab, is it? Yeah. Yeah, that is the main. That is a typical issue for first year university physics. The timetable for lab is very hard to synchronize with the lecture timetable, and most of the time is due to practical issue and stuff like that. So the previous university I came from, where I taught, also is the same thing. They do the lab first and then they learn the theory later. So yeah, no choice. It's very hard to avoid this. 6.3.1. Okay, so let's work out an example. Testing. 1, 2. Okay, working. Where's the example? Here. Okay. Yes. So before I joined XMUM, I was teaching in Singapore, National University of Singapore. Okay. So an electric motor exerts a constant 10 Newton meter torque. So this is a unit of energy. But see, if it's a torque, we don't call it joules. We call it Newton meter. Yeah. So let me copy down the information as we read to save time. So the torque is 10 Newton meters, acting on a grindstone which have a moment of inertia of 2 kg meter square about its shaft. System start from rest and find the grindstone kinetic energy at 8 seconds, find the work done, and find the average power. So let's do that. Okay. Okay. So yeah, so starting from this information, we just want to find the kinetic energy at 8 seconds. So how do we get the kinetic energy at 8 seconds? To get kinetic energy, we need angular velocity. We don't know angular velocity. Well, we have the torque. So from torque, we can get alpha. And from alpha, we can get omega once we know the time, right? We are using the kinematic equation. So let's start with the torque. Okay, and then alpha is just the torque divided by I, for which we have all this information here. So it's just it's a constant basically, and it's equals to 5, right? Radians per second square. And then using the kinematic equation, I can get omega. So I have initial omega plus alpha t. Once I got omega, I will use it to find the kinetic energy. So from here is the system start from rest, so initial omega 0, and alpha is 5, which we just calculated. And then we want to know what's happening at 8 seconds. So we can use this to calculate. So it's 40 radians per second. Okay, so once I got omega, I can get a kinetic energy, which is just half I omega square. So it's just half times 2 times 40 square. So the answer is 1600 joules. Okay, so that is the kinetic energy of the system at 8 seconds. And then the next thing is we want to calculate the work done during this process. So, well, you can get the torque and then you can integrate torque I alpha, but we can also use the work energy theorem. You can use the formula to find work, which is what I'm saying, right? You can use the formula to find the work done, but it will be faster to use the work energy theorem because the work done is the final kinetic energy minus the initial kinetic energy. We found the final kinetic energy is here. Initial is starting from rest, so it's 0, right? So the answer is the same as also 1600 joules. Okay, so remembering the work energy theorem will help you save time. And based on experience, past students usually, you know, when they want to do this, they are tempted to plug in the formula. They can do it, they get a correct answer, but maybe it wastes time, right? So then finally we want to find the average power. Brightness, yeah, average power is just the total work done over the total time, because it's average, right? So it's average, so it's just the whole thing divided by the whole time taken. And we have found the total work done to be 1600 and total time is 8 seconds, so it's 200 watts. You can also use torque times angular velocity, but angular velocity is changing throughout the process, so but it doesn't help you find the average, right? So you can get an instantaneous power if you want through this way. Okay, does anyone have any question? That without that. Yeah, so the math students are feeling lucky not having to do lab, is it? And the problem is MCO. Yes, we have to do everything online, including the lab, which is weird because lab is supposed to be physical. By definition, it's supposed to be physical, right? You actually do things, but you know, MCO and make it online. And one of the many reasons that 2020 is weird. Okay. So so there's no other question. Then we still have plenty of time left. So yeah, I still don't want to go back to the moment inertia. Let's do 2020. We've been hearing that growing up, right? So again, the China student don't know what we're talking about. Wawasan 2020. So for the China student, it's like, you know, over the past 30 years, right? The country has a vision that 2020 is a objective to achieve some major goals and things like that. And 2020 is like a year that Malaysians always look forward to. Like we work towards to making this place a achievable success or things like that. But 2020 actually came, and now is this happening. Okay. So yeah, so we spent about 10 minutes talking about angular momentum. Okay. MCL, what is omega plus omega alpha t? Are you asking me what is this formula? We have done this. This is kinetic formula. This is a kinematic equation, right? We have done this omega constant, right? So alpha, if alpha is constant, then and it's also d omega dt, then omega is the integral of alpha dt. So it's from alpha t plus a constant, and then if omega is omega 0 at t0, that will give me c equals to omega 0. So omega is omega plus alpha t. This is the kinematic equation, right, from high school. Now it's too bright. Okay. So now let's talk about angular momentum. So for angular momentum, so what have we transferred so far? We have transferred displacement, velocity, acceleration into angular displacement, angular velocity, angular acceleration. All right. We have talked about kinetic energy. Then we understand the idea of rotational kinetic energy, and then we talk about torque. And we, in terms of rotation, right, is the rotational version of the linear force. Then now we do it for momentum now. So the sixth thing that we want to convert to rotation, the concept of momentum. Linear momentum in the rotational sense is called angular momentum. So let us understand again, starting from the case of the point particle. Okay, so and point particle, I'll just call it PP because when writing is wasting a lot of time. Now, let us define the angular momentum of a point particle. Angular momentum of a point particle, PP, is given by this formula. So we will call this symbol L, right? And just like momentum is a vector, angular momentum should also be a vector, and it is defined as the position vector cross product with the momentum vector. Okay, so this P is the standard linear momentum, this R is the position vector relative to the axis. Okay, because when I talk about rotation, right, there's always going to be some axis, and usually we always say the axis is the origin of the coordinate system, make it easy. Then this is the position vector. Okay, so let's say I have some object, right, going in circular motion. Okay, so this is the axis of rotation, right, and then this is so my some coordinate system, doesn't matter, and then my particle is moving, okay, at some motion. And this is the interesting thing, you can define angular momentum even though the particle is going straight, because as long you just need a velocity. So if I have a velocity, I can get a momentum. So if the mass is m, then it's mass times velocity, and then I can get the position vector r. Okay, so r cross p will give me my angular momentum. So this is my angular momentum, and so this is r cross p. So we do the same thing, right? So we move the vector here, and then the angle is phi. We can calculate the cross product using the right hand rule, and then we get the magnitude. So the direction is, you get it using the right hand rule, same as before, right? And then the magnitude, okay, the magnitude of L is, I just call this L without the arrow, and then is the same as the magnitude of the two vectors sine of the angle between the two vectors. So L is equal to, this is m times v, right? So this is mvr sine phi. Okay, and in particular, if my angle is 90 degrees, then my angular momentum is just mvr. Okay, so so basically that is the angular momentum. Okay, so for example, right, we can talk about the angular momentum. For example, angular momentum of a particle going in circular motion. Okay, so this is like any motion, it doesn't have to be circular, but if it's specifically circular motion, then we can calculate, it is mvr. Okay, so let's say the tangential velocity is v, right, the radius is r, so this is 90 degrees, right, so it's 90 degrees, then L is equal to mvr sine 90, or pi over 2, then this is just mvr. Okay, so angular momentum of a particle going in circular motion, right, so the mass of this particle is m. Okay, so this is example 1. And then I have another example, right? Angular momentum. So this might be strange for some of you, but we can also calculate angular momentum of particle going in a straight line. Test. How's my sound? Test. I'm recording and still recording. In general, angular is just r cross the original one. Yes, correct, exactly. Yeah. So the force and the torque, right, is the original linear concept, just r cross it. So that is the basic idea. Okay. So now we can calculate angular momentum of a particle going straight. So let's say this is my axis. Okay, my Cartesian axis. So this is my origin. Okay, my origin, but my particle is over here, and it is just going normally straight, mv, right? So mv. So this particle is going straight, but even if it's going straight, we can give it an angular momentum relative to some point, which we call that axis, right? Because once we have an axis, we can define the position vector r, right? So then the angle between this vector r and this is phi. Okay, so the angular momentum, at least the magnitude, is mvr sine phi. And then we notice that if this is phi, right, and then this is phi, so this is phi, and then r sine phi is just the perpendicular distance. Perpendicular distance from axis. So L is equal to mv times the perpendicular distance. Okay, so for any object, right, any axis, and then for any particle moving in this way, then you just need to calculate the length here, and you can calculate the mvr, the angular momentum of a point particle going in a straight line. Okay, yeah, so any questions so far? Okay, yeah, so this is the introduction of angular momentum, and yeah, there's a few more things to talk about it, but I guess, you know, now time is up, so I guess we can continue in the next class. Does anyone have any question? Yu Chen, you are here. Yeah, Yu Chen. So I was looking for. I sent you an email. Can you check? Right, and then yeah, because I was looking for you. Axis is the origin. Yes. So in the picture here, right, the origin of the coordinate system is called the axis. Even though I have a particle moving, basically any point, right? If you have a fixed point, and then any object moving relative to that point will have something to do with the angular momentum relative to that point, because our angular quantities must refer to an axis. Okay. Yeah. So is Yu Chen here? Yeah. I'm waiting for him to respond. Okay. Okay. Yeah. So I think that's about it, right? Any other question? Online lab. Yeah, so that's yeah, if there's no other question, then that's all for today. Yeah, let's stop the recording. yeah, let's save the files before things get worse. So I'm going to stop the recording here.